Here's a few notes about kinetic energy. Number one, we define kinetic energy, or in other words, energy of motion, as a quantity we can calculate by taking 1/2 multiplied by an object's mass times its speed squared. Kinetic energy is therefore always a positive value. So consider somebody who's running to the right. If we have a coordinate system where we say to the right is positive and to the left is negative, then this person's velocity is positive. They certainly have a positive amount of mass, so their kinetic energy is 1/2 times a positive value of mass times a positive value for speed squared, and all this comes out to be a positive value. Now take that person running at the same speed to the left, and we have kinetic energy is 1/2 times some positive value of mass times some negative value for velocity squared. But because it's squared, that still comes out to be a positive value. So indeed, kinetic energy is always some positive quantity. Now, changes in kinetic energy can be negative. If somebody slows down, they have a decrease in their kinetic energy. So delta K is negative if something slows down, and of course the change in kinetic energy is positive if the object speeds up. Another thing about kinetic energy we need to keep in mind is how the value of kinetic energy depends on speed. We could summarize like this: kinetic energy is proportional to velocity squared. So let's focus on this idea that velocity is squared in these calculations. So let's say there was a child who kicked a ball into the street and then went running after it. So this car skids to a stop in order to avoid hitting the child who chased the ball into the street. And let's consider then 3 cases, right? How about the first case in which the car is only going 10 meters per second, which would be about 22 miles per hour, which is about the speed cars ought to go in residential neighborhoods. So the brakes lock up, and therefore the wheels don't just roll on the ground, so it's not static friction. Kinetic friction takes place as the wheels slide across the ground, and so some skid marks are left. Unfortunately, the car comes to a stop before it hits the child, and we'll just say this distance is some value d. All right, well, work is being done by the force of friction. Let's picture a free body diagram. The ground pushes up on the car, that's normal force. Gravity pulls down, so that's the weight of the vehicle. And then there's a friction force pointing back to the left, that's F. Friction force is mu times N, and in this case, N equals mg. So we have a force of mu mg. So this is a constant force, right? As the car slows down, it doesn't weigh any more or less, so the normal force is always the same, and the friction force remains constant during the braking period. So the work done is negative simply because the force points to the left while the displacement points to the right. So we'd be taking the cosine of 180 degrees in our calculation of work. Negative work just means that the vehicle is going to slow down as it skids. So the amount of work, the magnitude of that work, is equal to the force of friction, which is constant, times this displacement d, and in the end that has to equal the change in kinetic energy, which is 1/2 mass times initial velocity squared, right? The final kinetic energy is going to be 0 because they stop. So basically we have an expression that says force multiplied by distance is equal to 1/2 mass times initial velocity squared. But the force is constant, the mass is constant, so basically now we have the distance should be proportional to speed squared. So in case 2, if the car was going twice as fast, 20 meters per second, somewhere more like 45 miles per hour, which cars sometimes drive in residential neighborhoods, is definitely speeding, but sometimes people get in a hurry. Well, heaven forbid a kid runs out into the street to chase a ball with the car going that fast. How long are the skid marks now? Well, they're definitely going to be longer because the car goes faster. So let's say that's the distance d. So are the skid marks now going to be twice as long, 2d, because the speed is twice as great? No. Distance is proportional to velocity squared. And so the skid marks are going to be 4 times the original length, right? So what would happen if a car were driving even faster? 30 meters per second. So going more like freeway speed in a residential neighborhood. Then how long would the skid marks be? I think you can argue that the skid marks, if we call this d not the original distance when the speed was 10 meters per second, then we find in this case the distance of the skid marks would be equal to 9 times the original distance, right? The same argument can be made when hammering nails into wood. If the friction force between the nail and the wood as it drives in is a constant force, then the question might go something like this. If the hammer is swung with some speed v initial, and it takes something like, I don't know, you have to tap it 16 times to drive it in, right? We don't want to swing too fast because then we lose our aim, so we tend to swing the hammer slowly, but the slower you swing it, the smaller the amount of force, and so we often tap, 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 tap several times to drive a nail into a piece of wood. If you wanted to change it from 16 taps to be able to drive it into the wood with just one giant swing of the hammer, how much faster would you have to swing it? I think you can argue that the speed would have to be 4 times the original speed because kinetic energy is proportional to velocity squared. So if the velocity goes up by a factor of 4, the kinetic energy goes up by a factor of 16. Okay, so work is equal to change in kinetic energy. So if the kinetic energy goes up by a factor of 16, then the work done can go up by a factor of 16. So you can overcome the same frictional force with that many fewer taps of the hammer on the nail. So just some insight into kinetic energy. Make sure you appreciate this proportionality between work and kinetic energy and speed, and certainly make note that kinetic energy is always a positive quantity. Oh, and one last thing about units, right? What are the units for kinetic energy? We're multiplying kilograms times meters per second, and that gets squared. So we're going to have kilogram meter squared per second squared, and we can call that a kilogram meter per second squared times a meter, but you recognize that as newtons times meters, which should be joules. And of course, right, it's a form of energy. Work and energy are both measured in units of joules. Thanks for watching.